Okay, now we're recording. Um, but anyway, it's really great how active you guys are. Um, I'm looking forward to see how office hours go when they start next week. Um, we don't have a TA in the classroom this morning, at least not for the initial part. So if you have a question, make sure uh, jump in, throw something in the chat, but you know make sure to get my attention, right? You won't be you're not going to be um, interrupting me, right? Well, I guess by definition you will be interrupting me, but it's not uh, a big deal. Okay, so on Wednesday, I'm getting everyone whiplash by flipping through this so fast. So on Wednesday, we went through, we looked at the free energy of a system, primarily the Gibbs free energy, because most of the things we care about um, is at constant volume rather than, constant pressure rather than constant volume processes, because we tend to deal with um, either atmospheric or a controlled environment. And we got into the subject of equilibrium, and we said equilibrium is where the Gibbs free energy is at a minima, where we're at a critical point. And we differentiated between a global equilibrium and a metastable equilibrium, and said that a system can translate from a metastable equilibrium to the true global thermodynamic equilibrium if by having some fluctuations that can get a local region over this activation energy barrier, this activation hump, in which case, now that we have a small region of it nucleated, we can transform the whole system over to the minimum. We didn't talk about any mechanisms about how that could happen or how long it would take to happen. We just basically said that given sufficient time, this could happen, and most likely will, and that the height of this hump is going to be a function, or the time it takes to transform is going to be a function of how high this hump is. And then we looked at the thermodynamic variables of some single component systems, and we said if we have a single component system, the phase that's going to be is the one with the lowest free energy. And we also set up some things we're going to do in the future, and basically said this difference in the Gibbs free energy of the two phases is the driving force for the phase transformation. So at equilibrium, when the Gibbs free energy of in this case, the solid and liquid are equal, we're not going to transform. We actually have to get some undercooling so that we have appropriate driving force. For nucleation, we also talked about pressure effects, that pressure will change the equilibrium. And we essentially talked about that pressure effects, as the pressure increase, we tend to favor more close, more closely packed structures, right? And increasing the pressure will tend to expand the range at which close packed structures are stable. I also sort of threw out a question that we didn't have a chance to answer. Where did it? There was a question, I threw out a thing about high pressure phases, BCC high pressure phases in aluminum, right? And aluminum is a FCC metal, so it is a close packed metal, right? Why then would the high pressure phase of aluminum be BCC, which has a lower packing factor? Anyone have any speculation on that? This was something that bothered me for a long, long time until some people who do atomistic simulation, atomistic modeling, did the quantum mechanical calculations and came up with sort of a definitive answer. Anyone have any speculation? Well, it does sort of have something to do with electron energy states, sort of. It's a little more mundane than that. And the answer, it makes perfect sense once you know it. If you look at the number of second nearest neighbors, right? In a close packed structure, maximizes your number of first nearest neighbors. BCC actually measure, you have a higher number of second nearest neighbors, and when you put a large pressure on it and compress them, you actually, your total density, your total electron density increases. So you actually have a higher number of possible states in BCC at high pressures. But then at standard pressures, that effect goes away. Okay, so the last thing in this lecture that I didn't get to on Wednesday is the driving force for solidification. And this I had talked about before, in that we need an undercooling, right? And the Gibbs free energy change is the driving force. Right, so if we start at a high temperature, of course, the liquid phase is stable, and there's nothing we can do to make it solidify, right? You cannot freeze water above its melting temperature, right? There's not a thing you can do. Most things you could force to solidify by increasing the pressure, but water is weird. It goes the other way. Right? But this concept of an undercooling is really important. Oops. And the driving force for a phase change is really important. I know I've said this like 14 times already, but this is going to be really critical going forward, right? Because as you can imagine, we can work through it sort of as a thought experiment, and then we can do the mathematics later. So at low undercoolings, we already said we don't have much driving force. Oh, shoot, hold on. The dinging. Oh, so if not everyone's hearing it. Yeah, if you go into settings, your Zoom settings, you can turn off the play the chime every time someone comes and leaves the meeting. But anyway, so if at low undercoolings, we have a, excuse me, large driving force for the phase change, right? A big Gibbs for energy change. So then why don't we have, how can we get locked into metastable states? If we have a huge driving force for change at low temperatures, why can we maintain high temperature phases in a metal even at room temperature, right? Because for metals and ceramics, right, the most common way of getting the structure, microstructure that we want is high temperature processing and then quenching. And by quenching, we lock in our phases of interest. If our driving force for change is proportional to the undercooling, why does the high temperature phase stick around?
Alloys?
Well, yeah. Okay, so James, right, does not allow time for diffusion. Exactly, right? As our temperature goes down, our atomic mobility goes down, right? So our mobility is going to be highest at the equilibrium temperature, right? But we have no driving force for nucleation. So that means we're not going to be very fast, right? We're going to come into a region here where we still have more good mobility and we have a decent driving force. And so we'll have a fast phase transformation in this region. As we cool down more, our mobility decreases, right? Our mobility decreases exponentially with temperature. So then we get into a region where we have lots of driving force but no mobility, and our phase transformation stops again. Right? So, okay, that was basically the whole class. Thank you. Thank you for attending. You can take the final exam now. You know, conceptually, that's really the big idea behind everything that we're going to be talking about. Okay, so we do have a little bit last thing here with this, with the concept of an entropy of fusion, right? If we are sitting at the equilibrium and we write out our Gibbs free energy equation and set that equal to 0, we can solve this for entropy, right? And this is the change in entropy from going from one phase to the other, and it's related to the latent heat of fusion, right? And so this gives you oh that was too much of an aside. Sorry, but for small, if we had small undercoolings, right, we can consider that the latent heat of fusion and the enthalpy of fusion are essentially constant with temperature, right? If T is close to Tm, and we're just going to assume that the latent heat is the amount of heat that we have to put in or take out for the phase change to occur is independent of the temperature, which is approximately true if we're not too far away from the equilibrium. We can calculate what the change in Gibbs free energy is associated with the phase transformation, right? And so we can see that it's going to be approximately equal to the latent heat, right, times the temperature difference divided by the T sub m, right? So that's a quick way, if you know the latent heat, we can calculate what the Gibbs free energy of the phase change, Gibbs free energy change when the phase changes, so this delta G. So this is going to be approximately equal to the driving force for the transformation, right? So something like water that has a very high latent heat, well, I didn't want to zoom in. Something like water that has a very high latent heat, right? There's a large driving force for the large Gibbs free energy change on heating. Okay, nucleation we talked a little bit about. We'll talk more about it later. Okay, so today's stuff, binary solutions, right? We're getting into the world of heterogeneous materials now. Okay. I just closed the top hat. If anyone comes in after this, it's a little late. Okay. So the free energy of mixing. So we have a thought experiment here, right? And we want to make a solid mixture, right? And so assume that these are a solid solution. So assume these are metal elements, right? We'll talk about ionic and covalently bonded ceramic and other materials later. But assume for right now that these are metals, and we want to make 1 mole of solution. So we're going to bring together XA moles of pure A, where this is XA is less than 1, right? These are mole fractions, so XA plus XB has to equal 1, right? And some of B, and we're going to put it together. And before we mix them, right, if they're still completely separated, the free energy, the Gibbs free energy is just a linear combination of the Gibbs free energy of A and the Gibbs free energy of B, right? But then if we mix them together, right, we have a huge entropy change, and we're also changing the neighbors, right? Here the white is A is completely surrounded by A and B is completely surrounded by B. But here we have A interacting with B and interacting with A and B interacting with B. So we're going to have a big, potentially a enthalpy change and an entropy change. And so our Gibbs free energy of our mixture is not just the average, the weighted average of the two components, right? We need to include this concept of the Gibbs free energy of mixing, right? We can have both an enthalpy and an entropy change, as I just said. The enthalpy change is the heat absorbed or evolved during mixing, right? In chemistry class, you called that the heat of solution, right? And you probably in high school chem did the experiment where you put ammonium nitrate in water and the flask got cold, right? Those are those instant ice packs, right? So in that case, there is a large delta H of mixing, right? And you're taking in heat from your surroundings to make the bonds. Delta S of mixing is the difference in the energy, or saying things wrong. The entropy of mixing is obviously the change in entropy between the mixed and the unmixed states, and it's mostly configurational, right? So what's actually going on when you make a solution, when you make an alloy, when you make a polymer blend, is actually fairly complicated, right? So we're gonna do some simplified models, right? And first we'll talk about what's called an ideal solution model, where we ignore the enthalpy completely. And we say it's all due to entropy. Then we'll talk about the regular solution model, where we say, yeah, there is an enthalpy term, but it's kind of small, and we're going to approximate it in a fairly simple way, right? We'll talk about polymer solutions in an upcoming lecture, and they make some slightly different assumptions because the bonding happens between the polymer chains. The interactions is primarily due to van der Waals bonds, and you have a large excluded volume by the polymer chain. So it's a little different. And then there's real solutions, right? Which the models get us a good chunk of the way there, but the real solutions are actually can be much more complicated. Okay, so for our ideal solution model, as I said, we're going to assume that the enthalpy of mixing is 0, right? So the change in free energy on mixing is only going to be due to the change in entropy. So delta G mix is equal to T delta S mix, right? And there's 2 contributions that we consider to the entropy of mixing, right? The first is the thermal entropy, the number of ways thermal energy or vibrations can be distributed in the solid, Okay. And the second is the configurational entropy, right? The number of arrangements in the particles in the solution, right? So if we don't have any volume or temperature changes on mixing, we can completely ignore this thermal, right? The thermal component. Any idea why? Why can I make this statement?
Without the energy, it means that there's greatly reduced entropy.
Yes, but let's see if we can, what's the mechanism behind it? Right? Because this will set up our discussion for regular solution theory. Right? So if we're ignoring the enthalpy term, right? Where is the change in enthalpy going to come from if I mix just by mixing two things together?
The change in enthalpy comes from new bonds forming and breaking, releasing heat.
Exactly, or absorbing heat, depending on the energy of those bonds, right? So
yeah, endothermic, exothermic, yada yada.
Right. So if there's no change in enthalpy, there's no change in bond energies in the solution, meaning that AA bonds and AB bonds and BB bonds all have to have roughly the same energy. Right? The bond energy. And if the bond energy is the same, the elastic stiffness of the bond stiffness is the same, which means that the vibrational modes for the bonds are also the same. So therefore, no change in vibrational states on mixing. So no change in thermal energy. And obviously, if the bonds are all the same strength, then we're not going to have any volumetric change either, right? Because the A and B atoms are all going to be at the same distance away from each other as they were before. Right? So in the ideal solution case, we not only ignore the heat of mixing, we're going to ignore thermal entropy, and we're going to ignore all the other contributions to entropy, and it's just purely configurational. Right? So we can calculate the entropy. It's actually really straightforward. We're just going to use the Boltzmann equation, right? And assume that all configurations of A and B atoms are equally probable, right? We can compute the number of states. Since we're dealing with one total mole of atoms, or one mole of solution, we have Avogadro's number of total atoms. The number of atoms of A is just the mole fraction of A times Avogadro's number, right? And then Stirling's approximation, right, which we talked about in a previous lecture, and the fact that Avogadro's number times Boltzmann's constant is equal to the universal gas constant, we get this expression for the entropy of mixing, right? And there's always a question is, okay, I've got a negative sign out front. Why is this going to be greater than 0? And that's because XA and XB are by definition less than 1, right? So the log of number, the natural log of numbers less than 1 is going to be negative times the negative sign up front gives you a positive change in entropy. And if this is the entropy, the Gibbs free energy is just minus T times delta S. So we have an expression for the change in Gibbs free energy of mixing that's just that comes directly from the Boltzmann equation, right? Okay, so if we have an ideal solution, we can plot the change in Gibbs free energy as a function of the amount of XB that we have, right? And so we can see that we go through a minima at exactly where the mole fraction of both is 0.5, right? That's going to be where we have the greatest possible number of configurations, right? And then it scales by temperature, right? So at absolute zero, this is right, this T here out front guarantees that the Gibbs free energy of mixing at absolute zero is zero because there's no entropy change. Okay, what about exactly at zero, the mole fraction of XB zero and mole fraction of XBB? So at pure A and pure B, what's the slope of this? Right, if I take the derivative of this expression where XA equals zero, right, what do I get? So in the limit that XB approaches 1, right, this has to approach infinite, right? So it's asymptotically approaching this axis as we get close to zero, right? That's not saying the change in Gibbs free energy is infinite. It's the slope, right? So the change has to be infinite, right? So essentially that tells you that you always have a tiny, tiny, tiny little bit of solubility from the change in configurational entropy. It might be really small if the energy, the enthalpy term is large, right? So that's why oil and water are never going to mix, right? The enthalpy is just, the energetics are completely unfavorable. But you do get a tiny little bit dissolved because of this entropy change and the fact that this slope is asymptotically infinite. So the total free energy change, this is just the free energy change of mixing, right? Not the free energy of the solution. So the total free energy change, we need to take into account the energy, the free energies of our pure substances and incorporate the Gibbs free energy of mixing. So it's basically taking this curve, shifting it up, each end up by the pure states, right? So we lose our symmetry, right? And the same trend holds for the changes with temperature, right? Okay. So moving on to the concept of chemical potential. Who feels they understand chemical potential? If you do, if you're really, really confident, throw something in the chat. Right? This is really a topic that confuses everybody when they first learn it. And it's explained really, really poorly in every book I've ever come across. It took me a long time to understand it. And so I'm going to present it in a slightly different way than what you've seen. And hopefully it will click a little bit, right? And the key word here is potential, right? What the benefit of the chemical potential is it tells us so much information about the thermodynamic state of a material, right? We can get so much information from knowledge of its chemical potential, right? It's going to determine the stability of substances, the tendency of to chemically react and form new substances, right? So chemical potential is going to be a go-to for telling us if I make a solid solution between two things, are they going to form a metallic alloy? Are they going to form a ionic intermetallic or covalently bonded ceramic, right? How fast they're going to, their tendency to want to transform to new physical states, the driving force for diffusion, their tendency to migrate from one spatial location to the other, right? And so if you just hear this, it seems like some magical number. And it is kind of magical, I guess, in some way. But all of this comes from the fact that it's a potential, right? And it's the same as other potentials that you've learned in physics, right? So a potential is a stored as the energy stored per unit of matter, right? So it's a potential is an energy intensity, right? So for example, everyone knows the electric potential, the voltage, right? Really, really well, right? It gives you the tells you the electrostatic potential energy for 1 coulomb of charge, right? So if I have a electric field that's defined by a voltage, if I put in a charged particle, I know exactly what it's going to do, right? Because I know this electric field defined by the voltage. It's the same thing with temperature. If I have a temperature field, right, it doesn't have to be homogeneous, right? I know the temperature essentially everywhere in my refrigerator, right? I know what's going to happen if I put in something warm into my refrigerator. It's going to cool down, right? And the rate it cools down is going to depend on where I put it in there, right? If I put it in a warmer spot in my fridge, it's going to cool down less quickly. If I put it in the coldest part, it's going to cool down more quickly and then potentially freeze, right? No one in this class, I think, has any problem with the notion of temperature as a thermal potential, voltage as an electric potential, or pressure as the mechanical pressure, right? We know exactly what's going to happen if I have a compressed gas in a sealed container, right? If I take the plug off, it's going to decompress, right? It's going to expand, and we know exactly in which direction it's going to expand, right? Chemical potential is exactly the same thing, right? It gives us the intensity of chemical energy of a species in a solution, right? So just like the pressure tells us how a gas is going to expand, the chemical potential gives us a tendency for how quickly a species wants to leave the phase or the material that it's in, right? It's not much more complicated than that. All the other potentials in physics are named after the people who define them, right? So Kelvin, Pascal, volts, right? Volterra. Old white guys, that's right. But chemical potential is always just given joules per mole, right? There's a group of people who do solid state thermodynamics, and I guess you can count myself in there, even though I don't really do a lot of research in this area. But I agree we should give it an official SI name of Gibbs, right? So in some publications, you'll see the chemical potential given the unit of Gibbs, right? And as a reading assignment, I'm actually going to give you the original Gibbs paper where not both the Gibbs free energy and the chemical potential are introduced. There won't be a reading quiz on it or anything. It'll just be sort of a for fun reading. Okay, so how do we go from this define this potential field, right? That is this crazy idea of a chemical chemical potential. So it's just the amount of chemical energy, or the Gibbs free energy, possessed by 1 mole of the substance. That's it. It's the partial molar Gibbs free energy. What do I mean by partial? Well, it's the Gibbs free energy of a particular species. So in our binary solid solution, it's the Gibbs free energy of the A atoms or the B atoms in the solution, right? Divided by in 1 mole of substance, right? And we can define this concept of a chemical potential for homogeneous multi-components solutions, or for individual components, or the entire homogeneous, or even a heterogeneous mixture, right? And here's where the confusion comes in, right? It's always introduced through a technically correct but completely opaque and hard to understand definition, right? So this I took out of one of the solid state thermal books I have, right? I forget which one, probably Gaskell. The rate of increase in the Gibbs free energy of the system with respect to the increase of the number of moles of species I under constant temperature pressure, and constant number of moles for all species except I. Right? Does that tell you anything? All right. It just says if you parse it, if you take the time to go through it word by word, what this tells you is, if I have my solution and I add a tiny little bit more of A, it's how fast my Gibbs free energy changes if I keep everything else the same. If I add more stuff but keep the composition exactly the same, that's my chemical potential, which is not particularly useful and only makes sense in a differential way, right? I'm adding an infinitesimally small amount of something, so I don't change the composition of my solution, but I'm looking at how the Gibbs free energy changes as my composition changes in the limit of no change. It only makes sense mathematically. It makes no sense physically, right? Okay. What does make more sense is an analogy with other potentials, right? The application of an electric potential difference between 2 spatial locations results in electric conduction, the transport of electric charge. Imposing a difference in temperature between 2 locations leads to entropy or heat transfer from high temperature to low temperature regions, right? The difference in chemical potential between 2 locations, or a chemical potential gradient, is the driving force for the migration of chemical species from regions of high chemical potential to those of lower chemical potential, right? So in 2010, when you talked about diffusion, you talked about what's the driving force for diffusion? Change in concentration, right? You diffuse from regions of high concentration to low concentration. Well, that's not entirely true. You diffuse from regions of high chemical potential to low chemical potential, right? Phase changes in composition on phase separation, on phase transformations, right? if you look at the phase diagram, right, you might go from phase A at one composition to phase B at a different composition, right? And that's why you need your level rule to figure out what the composition of the phase at the temperature you're at, right? That change in composition is driven by the fact that I can lower the chemical potential of my species by making a change in the phase compositions, right? So it's exactly analogous to voltage or temperature. The chemical potential tells us where the atoms want to go or where the molecules want to go, right? So it's a measure of our system to do chemical work, the chemical pressure of our system, so to speak, right? And if you keep that concept in your mind, it becomes a much more useful thing than just a tool for algebraic manipulation of a couple thermodynamic equations, right? In fact, if you learn only one thing this semester, this would have to be the thing that I at least would hope that you take away. Is chemical potential is not really this crazy weird thing. It's just expressed that way, and a good physical picture of what the chemical potential actually means. Okay, so now we have to define it mathematically in terms of the or other thermodynamic variables, right? And I'll try and go back to the analogy of other potentials as we go through this. Okay, so what we want to know is how the free energy of a mixture will change when we alter the composition. So if we put in a vanishingly small quantity of A, and we add this to a large amount of our solution or heterogeneous phase at constant temperature and pressure, then the size of our system is going to go up by some differential amount, some vanishingly small amount, and the total free energy, right? Notice total free energy is emphasized here, is going to change by a very small amount, dg, right? And this small amount, we're going to say, is linearly proportional to the differential amount that we put in, right? On the big picture, the relationship between Gibbs free energy, the Gibbs free energy composition curve was curved. It was that parabolic function that we saw before. Well, it's not formally a parabola, but you remember what that picture we had before. But if we zoom in really, really small, we can linearize it, right? And so what this tells us is this chemical potential is the slope or the derivative of the Gibbs free energy curve at constant temperature, right? But it's, as I said before, if we look at the units, it's a partial molar Gibbs free energy. This has units of joules per mole, right? So anytime we consider something that's a Gibbs free energy per unit mole, it's actually a chemical potential. That's something else that never really gets discussed, and I'm not sure why. It was like my mind was blown when I had that realization many years after I took my last thermal class. Was anytime we talk about Gibbs free energy per mole, we're actually talking about chemical potential. Okay, so for a binary solution at constant temperature and pressure, we can assume that the contributions from the chemical potential are additive. And if we allow the pressure and temperature to change as well, we can correct that with an entropy term and a VDP term, right? So this is assuming pressure change at constant volume right now. And so if we think in terms of the molar quantity, we know how to, we can show us how to scale our system, right? We can take the mole fractions, right? So the Gibbs free energy of our mixture is just the chemical potential of A times the mole fraction of A, plus the chemical potential of B times the mole fraction of B, right? So that's the total thing. And this seems like an overly simplified equation, right? Because you're going to say, well, what about all that entropy of mixing that we considered? Well, these chemical potentials, this is the chemical potential of A in our AB solution. So this already takes into account our entropy of mixing and our enthalpy of mixing, right? So if we know the chemical potential of a species in the phase that it's in, we know everything there really is to know, of interest at least to us, right? And that's why it's so powerful, right? Are the heavens opening up? Do you see the rainbow and the cherubim yet? Or am I just going off on some crazy old man rant? I don't know. But this really is, I think, an insanely beautiful thermodynamic concept that doesn't get the love that it should, especially from students, because everyone's like, what the heck is this? Okay. So we can work through the math, but I think it's easier if we think about the picture first, and then we can just say, oh yeah, these equations actually mean that. So if we have, this is the Gibbs free energy of our solution, right? And we go anywhere on the composition, this composition curve, and we draw a tangent line. And we extend that tangent back to pure A and pure B. The interception here is the chemical potential of A in our solution, and over here at point D is the chemical potential of D in our solution, right? And you can go through the algebra and see that right here, right? Right? Here's, if we consider, well, we could plot it on a log axis and then we get a slope here, right? But if we think about, we do a change of variables and we make ln xa a variable and we plot this on a semi-log plot, and we can rearrange it as the Gibbs free energy over here, right? The chemical potential is our intercept. I said that in a little bit of a confusing way, I'm sorry. But you can do the algebra and it's pretty straightforward. So now what happens as we shift to smaller and smaller concentrations, right? At the ends, it's not as clean. That's where we're going to right now. So as we shift to lower and lower concentrations, what happens? What happens to the chemical potential of B? In the solution, right? It approaches the Gibbs free energy of B, right? What happens to the chemical potential of A in B? It's really, really low, right? Draw a tangent down. Super low, okay? So what does that tell you? Right? Remember, this asymptotically approaches at an infinite slope, right? So if I'm at pure B and I take a tiny, tiny amount of A, that's currently at the Gibbs free energy of pure A, and I put it into my solution B, my chemical potential of A in my AB solution is super, super negative, right? It's pointing way down here, right? So that means I'm going to have a huge driving force to dissolve A into my solution at low concentrations, right? So my dilute solution is going to dissolve. My A is going to go into B. That's why it's very, very rare. You don't have things that are completely immiscible. You might have a tiny little bit of solubility, right? Because you can't get around the fact that we have the entropy of mixing as being infinite. So we have this infinite slope here that shows in this tangent for our chemical potential, right? So this distance here, right, this minus RT natural log of XA, I'm sorry, there's a trash truck coming down my street. So you guys might get some noise from that, right? This term, this minus RT ln XA term, is really related to the chemical potential, right? So what this tells you is the state of the material of A in the AB solution, how happy it is, versus the pure substance. In this case, A really wants to be in the solution rather than being pure A. Right? So the difference between the Gibbs free energy of pure A, and the chemical potential of A in solution AB, right, tells you how stable A is in this solution, right? Okay, so time's up. We're going to go. I just have one last question since we're still talking about ideal solutions. Is there any way in the ideal solution model that substances won't mix? And the answer is no. So in an ideal solution model, everything is perfectly soluble because everything is driven completely by the entropy changes. So on Tuesday, we'll talk about regular solutions where we include the energy of mixing. And then we can develop miscibility gaps and insoluble substances. Okay, have a good long weekend, everybody. We'll see you on Wednesday.